volume of a cylinder, the factor that we multiply r squared h by is pi. And here, in this formula, for the volume of wood in a tree, the factor is 0.2 times pi squared. And let's just compare how these would differ. Well, 0.2 times pi squared is about 9.87. If we multiply that by 0.2, we get about 1.987, or I can round that to about 2. Okay, which means that the factor that we're using for this formula is about 2, whereas the factor that we're using in that formula is about pi, which makes sense. The volume of wood in a tree is going to be less than the volume of a cylinder because of its shape. All right, so when we look at exponents, there's things that we need to do before we start to look at the laws of exponents. First of all, we're dealing with integer exponents, and an integer is a number that is a whole value, and they can be negative, include 0, they can be positive. So the set of all integers looks like that on a number line. All the negatives, all the positives. Integer exponents, when they're positive, they mean repeated multiplication. So that means that we're going to have n factors of a when we apply an exponent to a base. When we use 0 as an exponent, this is an exception. The result of this is 1 with the condition that the base can't be 0. So that means any base a raised to the exponent 0 is equal to 1. And finally, the negative integer exponent definition represents a reciprocal, and in this case the reciprocal doesn't change anything about the power except it makes the exponent positive. So when we take the reciprocal, we don't keep the exponent in negative form, we make it positive. So that's the only change that we make when we apply a negative exponent. Again, the condition there is that a cannot be 0. Makes a little bit more sense for the negative integer exponent definition, because if a were 0, then our denominator would be 0. Potentially. So and obviously division by 0 is undefined. It's not doesn't give us a defined value. Okay, so those are our definitions. We have the positive integer exponent definition, the 0 exponent, and the negative integer exponent definitions. Let's start looking at how to apply these integer laws. So you're going to be doing an investigate in class just to reinforce the laws which you've seen before. You're going to be looking at powers of products. You're going to be looking at the powers for quotients, which is a division of common bases, and then you're going to be looking at power of a power. Okay, and in each case it's going to lead to a summary of those laws. You should have this handout already, and you should fill in the definitions for positive, 0, and negative integer exponents. And then after the investigate in class, you'll be able to fill in the completed exponent laws for multiplying, dividing powers, and taking the power of a power. And I'm going to use this video to look at actually using the exponent laws. This practice worksheet is also part of your package, and we'll go through these questions together so you'll be prepared to work independently in class. All right, this is the first one. Number 6, this is out of your textbook, found on page 363. You're taking an expression, okay, and you're simplifying it. Now when you simplify an expression, you're trying to make it reduced in its appearance, but you're also trying to convert to positive exponents. So in the margin on page 362, you'll see this stated, and elsewhere in the section, that when you simplify, you have to convert to positive exponents. So that's where we're going to need to use our definition of negative integer exponent. And if we want to convert to a positive exponent, then we have to use a reciprocal. Okay. So in the first example, we're going to use the multiplying powers exponent law. We'll call this the product law. And in this case, the product law requires us to add our exponents. So we're going to add 5 and negative 2. So that will give us d cubed. We're not substituting anything here, we're just simplifying. In this case, b, we're going to be using, so a was the product law. B is power of a power, we'll call it pop law. Okay, so the pop law requires us to multiply exponents, which gives us negative 10. And again, that's not a positive exponent, so we're going to use a reciprocal, reciprocate the base, and make the exponent positive. C, here's a quotient, so we're going to use the quotient law. Quotient law requires us to cancel out powers of our base, so this is best done by subtraction. So we're going to get, in this case, be careful because the exponent in the denominator on the base is negative 3, so it's actually going to produce a higher exponent on our base. It's going to go up to c to the exponent 14. In D, since this is already reciprocal, what I would do, this may seem a little bit counterproductive at first, but rather than dealing with a negative exponent, which itself applies a reciprocal to a reciprocal, I would go back to the negative exponent from inside the brackets, and then I would apply negative 6. And now, in that case, the first step was the negative exponent. That's not a law, that's just a definition, so I can convert back and forth. In step 2, I would apply the pop law, power of a power. So negative 3 times negative 6 is positive 18. And another result of that, having gone back to a negative exponent, is two negatives multiplied give a positive. In E, we'll be using the product law again here. We just have to make sure that the bases are all the same when we add the exponents. We can't add them if the bases are not the same variable letter. So this would be n to the 4 plus negative 13 plus 7, which gives us n to the negative 2, which is 1 over n to the positive 2. In F, we're going to be applying the power of a power law followed by the product law. And a little bit of order is important here. We have to do brackets first. There's nothing to do in brackets, but we do have exponent on that bracket, so we're going to take w to the negative 8, multiply that by w to the 3 times 2, and that's w to the negative 8 plus 6, because 3 times 2 is 6, so that would give us w to the negative 2, and then that's going to be requiring us to use the negative integer exponent definition, which is 1 over the base to the positive 2. In G, we have a quotient here, so first we're going to apply the product law to the numerator, and then we're going to apply the quotient law to the whole expression. So the first step is s to the 5 plus 4 in the numerator, dividing that by s to the negative 3. That will give us s to the 9, subtract negative 3, which is s to positive 12. Okay, in H we have power of a power, followed by quotient. So this would be t to the 4 times negative 5 all over t to the 6. So that's t to the negative 20, subtract 6, which is t to the negative 26, which will be 1 over the reciprocal of the base to the positive exponent. Now all of this is done for the purpose of simplifying, so that if we have to substitute values, which we're doing in number 12, we can simplify first. All right, and this is a good strategy to use when you have lots of numbers to substitute. In A, there aren't that many numbers to substitute, so I might just use this as an example of using a strategy that just puts in the numbers first. So I'm going to substitute and then evaluate in 12A. So I'm going to put in 2, squaring it, put in -3 to exponent 4, put in 2 cubing it, and put in -3 to the -2. Now, when we do this, we've got 2 times 2, which is 4. -3 to the exponent 4 would give us 81. 2 cubed is 2 times 2 times 2, which is 8. And -3 to the -2 would be 1 over -3 to the +2. So we have 4 times 81 times 8, which we'll calculate out. And that's 2,592. Multiply that by 1 over -3 times -3 is 9. So that would be 1/9. And if we divide 2,592 by 9, that would be the same as multiplying by 1/9. Or you could use your fraction button in your calculator, and that returns 288 as a result. So we didn't really have to use an exponent law, but we did have to use the negative integer exponent definition. Okay. Now in B, I have enough values to substitute that I'm going to simplify first, and then I'm going to substitute, and then I'm going to evaluate. And in your feedback problem for this section, I'm requiring you to do both methods: simplify, substitute, evaluate, and then compare that to just substituting and evaluating, which might seem to be simpler, but it's a lot of numbers you're working with. My expression, which is a quotient, I'm going to apply the quotient law of exponents. So I'm going to take my exponent on x in the numerator and subtract exponent on x in the denominator, exponent on y, subtract exponent on y in the denominator, and finally z, subtract exponent on z in the denominator. So that's going to give me x to the 4th, y to the -1, z cubed. Now, since y has a negative exponent on it, if I simplify this, I would write that as x to the 4th times 1 over y to the +1, which is really just the reciprocal. So that tells us, you might want to pay attention to this, that when you see an exponent of -1, it is just the reciprocal. We saw that before with our definition of the negative integer exponent. Special cases when n is 1. Going back to our examples here, continuing on, this is multiplied by z cubed, and if we were to simplify this, we would have x to the 4th times 1 times z cubed all over y. Okay, and we think a little bit like multiplying fractions. We've got 3 fractions, we multiply across the top, write that as a common expression, and multiply across the bottom, which would be 1 times y times 1. Now when we substitute, our next step would be putting in 2 for x. Okay, so 2 for x goes in to the exponent 4, y is -3, and z is 5. So I'm going to put in -3, and I'm going to be just taking that value. So it would be 2 to the exponent 4, which is 16, 5 to the exponent 3 is 125, and divide that by -3. And I get -666.6 repeat. Okay. Oh. Dot. Okay. That's approximately equal to, and the last part here, again, I'm going to have power of a power applied twice, okay, and then follow that by the quotient. Now notice when the base has a number in it, we have to apply that to the number as well as the variable. So it's going to be 5 to the exponent 2. I'm going to think of that as 5 to the 1 times 2 multiplied by x to the 1 times 2. If we write an expanded form, it might be more natural to just see it as 5x times 5x, which is 5 times 5 and x times x. When we show it this way, a dot I'm going to represent as multiplication in between. We're going to have 2 to the exponent 3, again power to power applied to the number, and y to the exponent 3. Okay, all over 10xy squared. So that's going to give us 5 squared, which is 125. X times x is x squared. 2 to the exponent 3 is 8, and then y cubed. All over 10xy squared. 8 times 125 is 1,000. I can start to do the quotient law with my x's and my y's, just to combine steps here. So I divide my numbers, and I'll get an answer of 1,000 times x times y, which now is simplifying, and then substituting and solving would require me to put in, again, the value of x was 2, and the value of y was -3. So that would give us -6,000. Okay, so again, I think simplifying first before we put the numbers in at least allows us to practice the exponent laws, and in some cases it will actually make it easier. There are fewer numbers to substitute. When we finally get down to this step, we're only putting in 2 numbers, and the operations are relatively straightforward. We've also, in this case, just the way it turned out, the exponents were 1 and 1 on the variables, so the math was pretty easy. And sometimes that'll be the case. All right, in our last one here, we have x, y, and z appearing twice. So here in the first part, we have power of a power, followed by the product law. Okay, so we have x, y, z. If I was to actually show this with the definition of an exponent, I would have 4 factors of x, y, z, which is very tedious to write. Okay, and then I could have my x to the -5. And if I was to write that last part of my expression as using the negative exponent definition, 1 over x to the 5th times y to the 7th times 1 over z to the 5th, then I know in my numerator I have x times x times x, which is x to the 4th, which is what the power of a power would give. And I'll just kind of point out that inside the brackets we have exponents of 1 on x, y, and z. So that's where the power of the power comes in, is you're taking an exponent on something that already has an exponent. So we'd have x to the 4th, y to the 4th, z to the 4th, multiplied by 1, multiplied by y to the 7th, multiplied by 1. So this would be all over x to the 5th times z to the 5th. Now when we go to simplify a little further, we can get all of our y terms now, which would be 4 plus 7, and we'd have z to the 4th. Now maybe in that step some of you might have just started to do your quotient law with the powers of x and z, which again, that was one more a law I hadn't anticipated at the beginning, but it turns out it's necessary. So that's going to be x to the 4 subtract 5, y to the 11th, z to the 4 subtract 5, which produces x to the -1, y to the 11th, z to the -1. As we keep going with this, we see, oh, now by applying these exponent laws, we end up with the reciprocal of x multiplied by y to the 11th multiplied by the reciprocal of z. So now it's fully simplified. Okay, so fully simplified means positive exponents only. Okay, and now I can substitute at the next step. X equals 2, y equals -3, and z was also 5 from before. So I'm going to put in 1 over 2, -3 to the exponent 11, and 1 over 5. So we have a half times a fifth is a tenth, and -3 to the exponent 11. Because the exponent is odd, the answer will be negative, and that's one of those properties of exponents that when you multiply something an even number of times, it'll always be even, it'll always be positive. If it's negative and you're multiplying it an odd number of times, the sign stays negative. So our answer is negative, and I would take that negative 3 to the 11, and then I'm going to multiply that by a tenth, which would give me, dividing by 10 is the same thing, negative 17,714.7 is what that would be equal to. Okay, so I hope I've at least had a chance to practice the exponent laws. And again, going back to our investigate in class, it'll just be solidifying these laws for you so you have a chance to summarize them in your note. And then you'll be working in class in a group on questions 1 to 5, taking turns to make sure everyone in the group understands before you move on. Working alone, solving 6 and 8 to 10, and then I'm collecting number 13 for your feedback question. Hope that helped. We'll see you tomorrow.